We are team 1141 from Carleton College doing problem C, people ruin everything. First of all, the problem. So predator and prey populations generally form steady cycles. However, when humans enter a system, they impact species reproduction rates, predation rates, ability to find food, and prey response to predators, and do so differently for different species. For example, in a meta-analysis published in Science Direct, while predation rates for all prey species were found to be lower in urban environments, predation rates for birds in particular were found to be significantly lower than the rates of other prey species. In order to model these changes, we adapted a predator-prey model to have modified human parameters. So the model itself has a couple different parts to it. So we have growth in prey population, which includes prey population growth due to reproduction, which is limited by the carrying capacity, so it has logistic growth. And then we have the prey population being predated upon, which obviously subtracts from that prey population. Then for our predator population growth, we have predator competition, and we have predator population growth, which is also limited by the prey population. So here are all of our different parameters. As you can see, some of them depend on H, which is kind of our human impact. So those parameters will change when humans enter the system, and then change again when they leave the system, so we can measure that human impact. As you can see, all the different parameters impact the different parts of the model in different ways. So our different parameters include reproduction rate, competition between prey species, the rate at which prey species is being fed upon, the number of offspring a well-fed predator would have, competition between predator species, and the efficiency of predators. And as you can see, the first four are the ones that in particular depend on humans based upon the research that we conducted.
But this is too many parameters to be able to examine the full long-term effects of the model with by fiddling with them each independently. So we use the tool of non-dimensionalization to reduce the number of parameters by clustering them into parameter groups so that we can kind of get an X-ray of the dynamics of the system in the long term, winding up with these parameters alpha, beta, and p. And in analyzing these parameters, we can actually come up with a conclusion about how our model is asymptotically stable in parameter space. One of the advantages of the model that we used with its constraints on the efficiency of predation is that it is asymptotically stable versus kind of the neutral stability of logical Volterra. Our system has a preferred amplitude that cycles with predator and prey populations, and so just a little nudge will wind it putting back on that asymptotically stable cycle. And what this animation shows is the region of alpha and beta that result in a stable, asymptotically stable cycle based on p. So here p varies between 0, when there's pretty much nothing on the graph, to all the way up to 8 when it gets quite vertical towards the 0 value of alpha. So the baseline setup for the model we used allowed us to compare the various ecological effects to an asymptotically stable cycle that we usually see in the wild. So our baseline parameters here are a reproduction rate of 6, a carrying capacity in a way of 2000, this predator death parameter of 2, a number of predators born when they're well fed of 5, and this exponent that kind of defines the efficiency that looks at the carrying capacity and says that predation is 95% efficient when the when the populations are at carrying capacity. And these are combined through our non-dimensionalization recalculated into the parameters alpha, beta, and p. And here you can see our asymptotically stable cycle. So when our populations start outside of the preferred cycle, it winds up converging in, and when it starts inside, it winds up spiraling outwards into that with this unstable node, this unstable spiral emanating from the equilibrium in the center. So we might also ask if this model is structurally stable or not. And we find that it is when we slightly change the parameters and structure of the model by, say, including weak mutualism, where with human, in fact, the reproduction rate goes up by a little bit, as does the carrying capacity. We find that by, and also including this dynamic where with humans, predation gets less efficient, but then after their removal, it gets more efficient than it was in the first place because of the lack of predator response. So including just a little bit of this, we see that we wind up with dynamics that we saw in the baseline model still of an asymptotically stable spiral with humans, and then going back to the initial case, roughly speaking, when we remove humans. And then again, when we choose instead to have a disruptive human presence where they reduce the reproductive capacity of the prey species, and with similar effects on increasing the efficiency of predation after humans have left, we still wind up with these asymptotically stable orbits in our systems.
So now we can think about what would happen if we applied one of these to a more intense change for these systems. For instance, when thinking about small prey birds like pigeons or swallows, which were the species we found the most research for, we found that their relationship with human presence was very symbiotic. We found evidence that humans increase reproductive seasons of these birds, increase habitat and food supply, decrease predation, and decrease their predator response. So as you can see, they have a very a strong mutualism. It increases carrying capacity, increases reproductive rates, and initially at least decreases predator response before, once humans are removed, again increasing that predator efficiency. So due to learned anti-predator responses, should humans leave, we can see that reproductive rates return back, carrying capacity would return back, and then that predator response would change to its new value. And so the results from this, as we can see, is that when humans are there, we go into a spiral sink. So we stabilize kind of at an exact point, and we don't have as much variation in the system as we would like to see as part of that stable spiral. And we have more prey, or more more predators than prey. And then once the humans leave again, we return to something that has a stable orbit, but it's one that has much more variation than our initial system. So we kind of start with a large amount of prey, which then very quickly get taken back down almost to zero by very effective predators. And then because the predators die out, then they rise up higher. And we could imagine in a system that wasn't as controlled that this could easily lead to ecosystem disruption. Then, in a case where we have a stronger disruption, in this case we were thinking about a species that was highly impacted negatively by human impacts in a way that wasn't as much due to that predator response, such as eagles being impacted by human fertilizers. We can see that humans greatly decrease habitation, carrying capacity, and reproductive rate. And here we see that then the species in this case just dies out even after humans have left. So there's a significant enough of a human impact initially to disrupt that stable cycle, and even once we remove humans again, it still has a very strong disruption that ends up being permanent in the ecosystem. So expansions to this. If we had more concrete data, we could make stronger claims about what would happen to these different species, rather than just kind of making generalizations. Additionally, it would be interesting to see the way that more species, like multiple prey species, interact with this model. We could take more human parameters into account, or we could modify our model from a more complex predator-prey model, even than the one that we use, in order to try to be a little bit more accurate.